Hello, ladies and gentlemen, and welcome to this talk. My name is Pierpaolo Carlone from the Department of Industrial Engineering of the University of Salerno, member of the IMAST Consortium and partner of the RIGHTWEIGHT project. And my talk today is about a manufacturing process that is widely used in order to realize high performance and lightweight components and structures using composite materials. The name of this process is Pultrusion, and in my talk I will follow this agenda. So starting from some fundamentals about polymer matrix composite materials, so just what we need in order to go through the rest of this presentation. Then I will move to a more detailed description of the conventional pultrusion process, highlighting the equipment and tooling that we need, the mechanisms that are promoted during the process, and of course some challenges that are there, considering in particular also some new developments, new variants of the pultrusion process, concluding my presentation with some applications and of course some concluding remarks. So let's start from this point, from the material that we want to process using pultrusion. In our case, it is obviously a polymer matrix composite material. What we mean when we say composite materials? Actually, a composite material is given by the combination of two or more ingredients. These ingredients are typically identified as matrix and reinforcement. And these ingredients are combined together in order to provide some unique properties to the composite material itself. The idea of combining different ingredients in order to improve properties or compensate some drawbacks is not completely new. Also in the past it was quite common to mix together natural materials in order to realize bricks for civil construction. Of course, today the idea of an advanced composite material is a little bit more elaborated. You can see an example here. And this is related to a lot of developments that we had in the field of material science, material technology, and in particular to our ability of downsize the reinforcement material, reducing the presence of internal defects and improving its properties, and of course to the possibility of creating a very strong synergy between the reinforcement and the matrix. And this synergy is particularly happening at the separation surface between the reinforcement and the matrix, where we can see the so-called interface. Along the interface, pretty much everything is happening. We have the transferring of load. We can create some energy dissipation mechanisms. So what we need when we want to realize our component is first of all to work on this interface. And a proper interface is not just achieved mixing the different ingredients. We need a proper selection of these ingredients. We need a treatment of these ingredients in order to increase their compatibility. And finally, obviously, we need to put the different ingredients together. And this is what we do when we are processing our polymer matrix composite material. And regarding of the specific process that we are using, the concept is pretty much always the same. It's, implementation can be different. So for instance, you can see here an example of a resin infusion process, spray layup rather than end layup over there, or a process that is a little bit more elaborated, like vacuum bagging, and autoclave curing rather than filament winding, and our pultrusion process is the one that we can see here. The selection of the process is very relying on the shape of the component that we want to realize. That is the first aspect that we should consider, because it is quite natural to assume that each solution is more suitable for some shapes. But regarding of the specific process, there are 3 steps, 3 basic actions that we need in order to realize our component. And these 3 steps are the one that you can see here, given by the impregnation, the shaping, and the solidification. When we are talking about impregnation, shaping, and solidification, what we are saying is nothing else than the creation of the composite material, starting from the basic ingredients, the creation of the geometry that is achieved applying some external solicitation to our composite material, and finally the improvement of the mechanical properties by the consolidation of the matrix itself. So looking at these 3 steps, we can keep in mind creation of the material, geometry, and finally property. Now, as I said, regarding of the process, we should somehow follow this path. The way that this path is implemented is very sensitive on the behavior of the materials that we are processing. And in particular, it is sensitive to the behavior of our matrix material. When we are talking about a PMC, a polymer matrix composite material, actually we should consider that our matrix can be based on 2 different kind of formulations. From this point of view, it is relevant to make a difference and to understand the difference between a thermoset resin and a thermoplastic one. Now, starting from the microstructure, if we want to understand the difference between a thermoset and a thermoplastic material, let's start from this point. Let's imagine how they are constituted, at the microstructure level. So in the case of a thermoset, we can easily imagine that this thermoset resin is given by the combination of several single units that are called monomers. The different monomers will react and will combine to each other under specific conditions of temperature and pressure and with some catalyst in order to create, first of all, some chains, and then the different chains will start connecting to each other in order to achieve a 3-dimensional network. All of this is happening during a chemical reaction that is called the curing reaction. And our way of representing, of understanding what is going on during the curing reaction is actually depicted in this graph here. So if we imagine that at the very beginning we are starting with our resin system at some condition of temperature in liquid state, if the conditions are suitable for the activation of the curing reaction, this kind of, combination of monomers will start. Our measurement of the curing reaction is given by the so-called degree of cure. The degree of cure will range from 0 to 1. 0 means, the beginning of our reaction, and 1 means the 100% of reaction already completed. And moving from 0 to 1, there is a very important value of the degree of cure corresponding to a fundamental transition from the liquid phase to the rubbery phase. This transition is happening at a precise value of the degree of cure that is sensitive for each resin, and it corresponds to the so-called gelation. After gelation, our material will not be liquid anymore, will not be able to flow and wet our fibers. So if we want to achieve a proper impregnation using a thermoset material, this step should be completely achieved before the gelation. The gelation transition is a one-way transition, meaning that after moving from liquid state to rubbery state, we cannot go back. But the reaction will keep on going, and the degree of cure will increase if the temperature is a suitable one. Increasing the degree of cure will improve the mechanical properties of our material, and the second phase change that we can promote during this curing reaction, and most probably it will happen when we are cooling down our material, is the so-called glass transition or vitrification. In correspondence of this transition that is sensitive to both degree of cure and temperature, so we don't have just one value of degree of cure for this kind of transition, the phase, the status of our material will change from rubbery to a vitrified solid. And differently from what typically happens on gelation, this transition is not, a one-way transition. We can go back and forth, just calibrating our temperature. So, just, to summarize this, when we are dealing with a thermoset resin, if we want to improve our properties, we need to activate the curing reaction, heating our material. And what is particularly interesting when we are processing this kind of resins is that the viscosity of these resins at the beginning of the process is typically quite low, meaning that they can easily flow through our preform and wet fibers. The situation is quite different if we are looking at a thermoplastic material. From a microstructural point of view, what is missing here is the presence of that 3D network that I mentioned a couple of minutes ago, and the linear chains that are composing our thermoplastic material are weakly connected to each other. And this is quite interesting from the point of view of the reprocessability of the resin, meaning that we can just heat up our thermoplastic system, it will melt, we will have the possibility of shaping it again and again and again, and of course this is very interesting from the point of view of the recyclability and sustainability. The drawback here is that if we want to reduce the viscosity of the material, we should go really to high temperatures. The parameters that we need are, a little bit more severe if compared to what we saw in the previous case. Of course, depending on the specific resin system, we have different solutions for this kind of impregnation and for the wetting of the reinforcement and the creation of the interface. I would like just to recall the three fundamental cases. So we can talk about an offline impregnation, and in this case, typically the combination of matrix and reinforcement is completely decoupled from the shaping and solidification. This is what typically happens when we are working with prepregs. And also in case of pultrusion, it is the general case when we are processing some high viscosity thermoplastic resin. On the other hand, a completely different situation is given by the so-called online impregnation. In this case, the viscosity of the resin is, so low that we can easily promote some liquid flow and wet our reinforcement and create the interface that I was mentioning. There are also some hybrid approaches, and this is typically the case of commingled yarns, where the reinforcement and the matrix are shaped in the form of fibers, mixed together, but until the moment of the shaping and consolidation, we cannot consider that matrix is rigorously wetting the fibers. We should increase the temperature, we should promote some melting of our matrix fibers, and then the interface will be, created. Now, moving to pultrusion. In this figure here, you can see a very good representation of a pultrusion line. The word pultrusion is coming from the combination of two different words, pull plus extrusion, meaning that when we are processing our material by pultrusion, actually we are extruding it applying a traction load. So you can imagine that along this line there is a system that is playing more or less this effect that I'm doing with my hands, and this is typically the role of the pulling system that you can see here. And on the other edge of the line we have the dry reinforcement, and since in pultrusion the typical shape of the reinforcement is in the form of continuous fibers, you can imagine that this traction load is propagated along this line, and the dry reinforcement is continuously pulled through the different stations in order to achieve exactly the 3 steps I was mentioning before. So impregnation, shaping and solidification. At the exit of this element here, that is our heating and curing die, the complete pultruded material is a completely vitrified solid, and it can be easily clamped and pulled. At the end of the line, it is typically placed a traveling cut-off saw that it used, of course, to cut our profile at the desired length. So one good point about pultrusion is that the process is highly automated, very effective from the point of view of the usage of the material. The amount of scraps is the minimum possible. We are using pretty much all the material that you can see here, and all of this can be done with a very limited action of workers. In other words, if we want to run our process, we need just someone to check if everything is going fine there, and the same person can even check and control 2 or 3 or 4 lines at the same time. So this is what we are seeing here is the, let me say, the conventional pultrusion line, generally used to process a thermoset material using the open bath technique. The term open bath refers to the way the resin is introduced into this system, and in particular where the impregnation is taking place. This is already, let me say, a development of the original concept for pultrusion. At the very beginning, around the 50s of the previous century, the pultrusion line was not, prepared along an horizontal development. It was just, following a vertical scheme. So you can imagine more or less that the dry reinforcement was at the third floor and the final product was collected at the ground floor. Now, clearly, the scheme of the process is very different, and also the capability of this process are very different in terms, for instance, of architectures that we can use for our structural component. At the very beginning, most of the reinforcement, all the reinforcement was in the form of unidirectional fiber, so very good properties along the axis of our profile, but not so good properties in all the other directions. Now we are able to combine in the same profiles unidirectional fibers, mat, woven fabric, veil, and so on. We can use some braiding, so quite complicated arrangements for our reinforcement in order to tailor the mechanical behavior of our component. Over there you can see some examples of pultruded profiles. So, looking at this figure, we can imagine the pultrusion line as a sequence of different stations, starting from the first one that is represented by the krill rack. On the krill rack, the dry reinforcement is positioned, ready to be used, ready to be pulled through the next stations. Looking at these images here, you can easily see that we have the possibility of using different kinds of reinforcement in pultrusion, different kind of fibers, glass fibers, carbon fibers, and of course polymeric fibers and so on, but also different arrangements of the reinforcement itself. Clearly, the most simple shape is given by the unidirectional rowing or tow, but also some rolls with tape or mat and others are possible. What is quite important and regarding of the specific architecture of our reinforcement is that the dry material on the krill rack should be under a kind of pretensioning in order to keep the fiber quite straight, avoiding collision or interlocking and anything that can stop our line. Our reinforcement, just pulled out from the krill rack, will start some kind of preforming using the so-called guidance plate. These plates are drilled, and through each hole a group of fibers is passing in order to start some placing of the reinforcement in our cross section. So moving slowly, plates after plates, and following this kind of material collimation, organization of the reinforcement in our cross section. Once again, this is very important in order to avoid any mechanical interlocking of the fiber and keep with our process that virtually can produce a never-ending profile. At the end of the guidance plate, the impregnation step will take place. And in the conventional pultrusion line, this step is achieved using this open bath. Looking at the open bath, we can imagine this tank that is filled with catalyzed resin, ready to be used, ready for reaction, and the dry fibers is forced to dive inside this resin bath. So this is what we can imagine before going inside the resin bath, and after, at the end of the resin bath, the situation is more or less this one. So with the fibers completely surrounded by our resin. Of course, considering some limitations in terms of viscosity, this technique is particularly suitable for, if not limited, to thermoset resins. In the case of thermoplastic resins, the viscosity of the material is typically too high in order to have the same results. The temperature of the resin inside the open bath is obviously monitored in order to be sure that no reaction is taking place. Because, of course, considering that inside the resin bath we have really a high amount of resin, if any kind of reaction will start there, we will not be able to stop it. And once again, we will have some problems with our process. So another interesting point about the open bath is that for large production using pultrusion, the resin inside the open bath can be added continuously as soon as it is taken away with the fibers. And in order to avoid a layering effect, meaning that the old resin will stay on the bottom of our tank, and then we are going layer by layer, putting, a new resin, but different layers will have different histories. Typically, the fibers are forced to fall a profile, a path similar to the one that you can see here. So reaching the bottom of our open bath and then moving up and down again and then outside. This will create some kind of mixing of the resin and also will provide some kind of first in, first out strategy for the, the movement of the resin itself. Now, looking at the picture over there where the situation of the reinforcement and resin after the bath is depicted, you can easily see that when we are going out from the resin bath, the amount of resin that is surrounding each toe is generally much more than the resin that we need in our composite cross-section. And for this reason, after the open bath, some other tooling is used in order to, first of all, remove this excess of resin and also to force this surrounding resin to penetrate inside each toe in order to completely wet also the fibers that are at the core of each toe. This strategy here that is once again based on the usage of preforming plates is quite interesting also from the point of view of the environmental impact of the process, because the excess resin can be easily recovered and moved back to the open bath. And this will give us the opportunity of reducing the amount of wasted resin more or less to zero, and clearly also will give us some benefits from the point of view of the environmental impact. The impregnated toes are now ready to go inside the heating and curing die, and this die, that is actually the device that is providing the shape and is curing the material that we are processing, is typically realized using a rounded or tapered inlet. This particular shape that you can see here is used for two basic reasons. The first one is to avoid any damage to our fibers. And the second one is that using this kind of shape, we can naturally achieve an increase of the liquid pressure of our resin due to this kind of compaction. Now, why this effect is quite interesting. If we go back to the impregnated toe at the exit of the open bath, actually in that moment we don't have just resin and fiber in our system. There are also some portion of air entrapped in this combination of resin and fibers. And we should be able to remove this amount of air from the material, otherwise at the end of the process we will find some voids in our pultruded composite material. And since voids are the worst enemies of each composite material, if we want to achieve a good, strong product, we should remove these bubbles here. And here the effect of the inlet is very important, because actually if we have a look at the schematic that is there, we can imagine that the fibers behave like a porous traveling material. So they are moving inside the cavity, impregnated with fibers, with some air. And in this case, the resin flow and the air flow can be described and can be studied using the model that is depicted there. So a modification of the Darcy law, including also the velocity of the porous media. So this medium is traveling, and when the conical surface of the die is met at the intersection point, what we will have is some kind of compaction, an increase in pressure that you can see here, looking at these results from numerical simulations. And this pressure field push the air away from the cross-section, sending the air back. So the air volume fraction is the red spot that is there, and typically around the the tapered die inlet, it is quite common to see all these bubbles that are flowing away. And we are very happy in that case, because it means that the air is not going inside our cross-section. Now, more or less the same result can be achieved using an alternative to the open butt pultrusion. This was quite a urgent problem some years ago, because if we look at the open butt, what we have there is a reactive toxic material that is releasing some volatile compounds in the surrounding environment. And we know that emissions from reactive resins are not really good for the environment and are not really healthy. As an alternative, the open butt configuration can be replaced directly injecting the catalyzed resin inside the preliminary portion of our die, following a scheme that is depicted here. And as you can see, more or less the same stations that we were looking at before are there. So the krill rack, some preforming, but instead of the open butt, what we have here is an injection chamber. And typically this injection chamber is directly connected to the heating and curing die. So the rest of the line is pretty much the same, which is the idea behind this injection chamber. Actually, the internal part of the cavity is represented down here. So we can imagine that the dry reinforcement is directly going inside this chamber after the preforming step, and at some point of the chamber, the resin can be injected. This injection of resin will give us the possibility of wetting the reinforcement and achieving the impregnation stage just few seconds before moving to the shaping and solidification. The specific configuration of the injection chamber should follow this kind of schemes that you can see here, moving from the very simple one that is the tapered chamber, Then other possibilities are the teardrop chamber rather than high pressure or siphon chamber. So different possibilities that are designed in order to promote the same effect: compaction of the material, increasing of the resin pressure, and in order to promote some flow of the resin through the preform. But at the same time, what we should avoid is that the resin will flow back, flowing out of at the beginning of the chamber itself. So everything here is just a game of injection pressure and pulling speed. And what we need in order to obtain a good balance, a good calibration of this parameter is to combine them in order to completely wet our reinforcement without this kind of backflow. Just looking at what is happening inside the chamber, we can imagine this kind of scenario. So the colors there refer to the resin pressure. The injection is more or less in this point here, and due to the tapered shape, so the reduction of the cross section, what we are seeing here and moving on is a reduction of porosity, a reduction of permeability, so less space for our resin that should be pushed back, until some point. Once again, the increasing pressure that we are seeing in this chamber is very important to prevent the inlet of air and the presence of voids in our pultruded part. This pressure field will actually push away all the air that is trying to travel together with the fibers. So as a general rule, when we want to calibrate our parameters for a suitable, for a well-planned injection pultrusion process, we should try to increase the speed as much as possible, together with increasing the injection pressure. Of course, if the speed is too high and we are not pumping our resin at a suitable pressure, we can see something like this. So the presence of some empty portion in our composite profile. And of course, in that case, we are just producing some scraps. At the same time, the pulling speed and the resin pressure should be balanced in order to avoid that too much resin will go inside the chamber and this resin will not be captured by the by the fibers and will not move on inside the straight portion of the cavity, so a lot of resin will be wasted here. If we want to imagine which is the suitable combination of parameters, actually we should stay in the middle of this graph here, in this optimum processing region, avoiding any kind of black flow when the pulling speed is not really suitable and we are working with a high pressure, or when we are pulling our material too fast and pumping our resin at low pressure. Increasing the pulling speed will be reason for other problems like internal defects and, once again, the production of scraps. So regarding of the system that we are using, it can be the open bath impregnation system or the injection chamber. After this combination, the material should be shaped and consolidated. And this is what is happening inside the core of our pultrusion line, and that is represented by the heating and curing die. On this figure, you can see a realistic pultrusion process. So the die is basically this steel block with an empty cavity inside that is providing the shape to our cross section. the die is realized using steel, and in order to increase the durability of the die, generally the surfaces that are in contact with the workpiece are chromium coated in order to have a longer life and produce more meters of our composite product. The die is heated using several systems, such as steam or oil, but the most common one is based for sure on electrical heaters, like plates or cartridge, so just dissipating, using the Joule effect, some heat inside the die, and this heat will be then transferred to the processing material in order to activate the curing reaction and have some cross-linking and increase of the mechanical properties. So if we want to take a look inside the heating and curing die, we can imagine that something like this is happening. So the material is entering inside the die. At the very beginning, our resin is in liquid state, so we can think that here what we have is our impregnated reinforcement. The preliminary part of our die is generally at low temperature, because before the activation of the resin reaction, we want to be sure that the reinforcement is completely impregnated. So as you can see here, the heating system is moved a little bit away from the inlet, and in some cases it is quite common to have some cooling channels in this part of the die, just to keep the temperature at a good level and have some kind of a liquid zone that will guarantee the proper impregnation of the reinforcement. After this point, thanks to the heat that is provided by our heating system, the temperature of our material will go up and the resin reaction will be activated. So the different monomers will start reacting, and we will reach, first of all, the transition from liquid state to the rubbery state. So after a while, it means that inside our die, we will see some kind of gelation, and crossing this surface, the interaction of the material with the die will completely change. Because of course, at the very beginning, we have some viscous forces, solid with liquid interaction, but after gelation, both of the materials are kind of solid, so we can think that some kind of friction is happening there, also with some variation in the friction coefficient. And moving on inside the die, so let's imagine that the reaction is keep on going and our degree of cure is increasing at higher value, looking at the famous unit. And after a while, also the transition from the rubbery state to the solid state will be promoted. At that point, our pultruded workpiece is completely solidified, and due to the chemical shrinkage that is a common feature of thermoset resins, also some detachment of our workpiece from the die will happen, meaning that after this point here, we will not have any more interactions between the composite material and our die. In this figure, we can see some temperature profiles that are collected inside a composite material during pultrusion using the so-called traveling thermocouple technique, meaning that a thermocouple is connected to the fibers and will travel inside the injection chamber eventually, and then the heating and curing die, collecting in each time instant the temperature that is experienced by our material inside the die. Looking at this figure, we can see how the temperature inside the injection chamber is typically low due to the cooling effect that we were mentioning a few minutes ago. But after that, the cooling channels have been crossed. The heat provided by the electrical heaters will promote the increase of temperatures in our material there, on the surface first of all, and then in the center. This will provide the activation of the resin reaction. The resin reaction is typically exothermic in nature, meaning that further heat will be generated by the material itself, and according to the energy balance that is written here for our traveling material, combined with some other equations that are explaining how the material is reacting and how it is generated, at some point inside our die, actually the processing material temperature will overcome the temperature of our heaters. It is quite evident that after a while we don't have to increase further the temperature of the heating die. Otherwise, the heat generation inside the material will be the reason for an extreme overheating of our composite, and the resin, of course, will burn and will degrade. Several softwares are suitable to solve this kind of problem, and what I'm going to show you now is the simulation of the temperature and degree of cure looking at this L cross section. In this case, our profile is quite good in order to understand also something about the distortion of the material inside the heating die. Just a few words about our material. The reinforcement is a combination of unidirectional fibers in the core of this L, and then moving to the surfaces, we will have a combination of matte and woven fabric. So the real process is depicted here. It will give you a very good representation of what is going on. And solving this problem, we can see that at the very beginning, most of the action is happening on the external surface of our composite. Basically, this is related to the fact that we are heating our material using some heat conduction. So the surface of the composite is the closest part to the die, and it will be the first one that will experience this increase in temperature and the activation of the resin reaction. But after a while, when the reaction will be activated also at the core of the material, the situation will be completely reverted, meaning that the temperature inside the material will overcome the temperature at the surface, and this is referred to as the temperature crossover point, and the same thing will happen for the degree of cure. Higher at the beginning of the process at the surface, but after a while at the cure crossover we will have higher values of the degree of cure at the core of our composite, and clearly lower values on the surface. The proper definition of the processing parameters, anyway, is not just a matter of temperature and degree of cure. There are other aspects that deserve proper consideration, in particular if we are considering the stresses and strains that are induced inside the material when we are traveling inside the pultrusion die. As we have just seen from the simulation, when we are moving inside the die, some gradients in temperature and degree of cure are established. And these gradients are the main reason for internal stresses and strains. The proper consideration of these aspects is quite important if we are looking at the tolerances of our pultruded part. Once again, the virtual simulation can give us an idea of what is going on inside the material when we are traveling inside the die. So if you take a look at the red arrows there, it indicates the position inside the die. When we are inside the die, the material is heated, it tends to expand, but it is constrained by the cavity. But as soon as the material will go out of the die and this constraining will not be there anymore, all the internal stresses that are coming from the thermal expansion or the chemical shrinkage will be released in terms of distortion. And for this particular shape, a very good estimation of the distortion is given by the spring-in angle. So meaning the deviation from the 90 degrees that we use it to realize the cavity inside our die. So why the setting of the processing parameters is important, and why the general rule of increasing the pulling speed if we want to increase our productivity is not always the best approach. Looking at this graph here, we can see that if we are traveling along the line too fast, the vitrification point will be displaced to the die exit, and eventually we will have this vitrification outside the heating and curing die. And if this is happening, the amount of distortion will be much higher. As a general rule, it is better to have at the die exit a fully vitrified solid, so reducing the amount of distortions that the material can have outside. Also, apart from distortions, there is a huge impact of the pulling speed on the internal defects, because the local concentration of stresses will be the main reason for internal defects like matrix cracks or delaminations and so on. So moving from this image here to the others, what are we doing is just increasing the pulling speed using the same heating profile, and the amount of defects that is characterizing each cross section is quite heavy. But let's now imagine that our process is properly calibrated. We are out of the of the heating and curing die, so the material is solid, rigid, and it can be clamped and pulled using our pulling system. There are two basic devices that can be used for this purpose. The very simple one is the caterpillar pulling system. So you can imagine this rotation of the belt, some pressure applied on our pultruded profile, and everything is moved in the along this direction. Or as an alternative, we can use some kind of reciprocating pullers based on the combined actions of two grippers that are just clamping the workpiece, moving, and then clamping and releasing like this. In this case, the control on the speed, on the pulling speed that we can achieve is quite better, because typically we are able to avoid any slipping. The configurations that we just saw are quite common when we are processing a thermoset resin as matrix for our composite material, but some variations of the pultrusion line are necessary if our matrix material is represented by a thermoplastic resin. And this is mainly related to the fact that thermoplastic resins have a high viscosity at room temperature. They cannot be easily processed in order to have the impregnation stage. So, in the most common approach, the starting point of our pultrusion line is given by the same krill rack, but on that krill rack a combination of matrix and reinforcement is placed in the form of tapes or commingled yarns or toe preg, but basically both of them should be there. And of course, keeping in mind that in order to shape a thermoplastic material, we have to reduce, first of all, its properties by heating it up, and then cooling the material down will give us the improvement of the mechanical properties. Another variation is necessary inside the heating and curing die over there. So in this case, our pultrusion die is characterized first of all by the presence of a heated portion at the beginning of the die, where the material will be heated up, and this increase in temperature will promote some melting of the thermoplastic resin, some kind of flow and proper wetting. The eventual excess of resin will be wiped out, and then when the straight cross-section of the die will be approached, we can slowly start cooling down the die itself and the material. So more or less it is exactly the opposite of the situation that we saw previously for thermoset pultrusion, where the preliminary portion of the die was cooled down in order to avoid a premature gelation of the resin, and then we went up with the temperature. Now, in order to soften our material, we have to heat up the thermoplastic resin, promote some kind of flow, some further wetting of the fibers, and then we can move on with the shaping of the material and the cooling. Other interesting variants of the pultrusion line are given by the so-called curved pultrusion. In general, when we think about pultrusion, we are thinking about a rectilinear profile with constant cross-section, so a strong limitation for the components and structures that we can realize. So recent developments of the pultrusion machine enable us also to realize some kind of curved component, as you can see over there, using quite a different approach based on the usage of a moving, oscillating die that is actually moved back and forth in order to take more material inside and then move back, heating and curing the material. Of course, we cannot realize very complex geometries using pultrusion. So why this process is so important and why it is so used for manufacturing PMC. In this pie diagram that is representing the volume of composite classified by manufacturing process, pultrusion is with filament winding in the red portion, so quite a big one. And the reason for this wide usage of pultrusion can be found in the graph over here. This graph is representing the so-called energy intensity associated to each manufacturing process. And when we say energy intensity, we are referring to the amount of energy that we need in order to achieve 1 unit mass of product. And in that amount of energy, actually we are considering everything. So the raw material, the energy consumption during the process itself, storage, the labor that is there, everything converted into energy. And pultrusion is exactly here. So as you can see, it is quite a low energy intensity if compared to other processes like resin transfer molding or vacuum assisted resin transfer molding. There is more or less a factor of 5 if we compare these different approaches. And if we want to compare pultrusion with autoclave processing here or with pre-preg manufacturing here, there is more or less 1 order of magnitude of difference in terms of energy intensity, meaning that if you have your product and you are able to do it by pultrusion, you should be happy. If you have one product and you are not able to realize it by pultrusion, a good approach is to think if the shape of that component can be changed, if we can use an alternative design in order to make that component feasible by pultrusion. Pultrusion is nowadays used in several markets. Some of them are depicted here. Pultrusion is quite common for civil construction, automotive sector. Now there is a lot of interest also from the aerospace sector. And let me give you some nice examples of applications of the pultruded profiles. So rebars that should replace the steel rebars that are subjected to corrosion and other issues. Structures for restoration of buildings after earthquakes, structures for corrosive environment, or bridges and decks and other profiles that can be assembled together and can be installed very easily if compared to other solutions. So pultrusion has a lot of application in the civil sector, but some interesting application of pultrusion can be found in the energy sector. So for instance, for harvesting solar energy or wind energy using different approaches depending on the specific wind turbine that we are looking at. Something more, applications in automotive, and here you can see also some interesting examples of curved pultrusion, for instance for bumpers over there, or leaf spring here, or some supports for battery packs that are quite important for the new electric mobility and so on. But if you just take some minutes and surf a little bit in the internet, you will find thousands of applications for pultrusion process. So we are at the end of this presentation. I truly hope that I was effective in commenting on the pultrusion process and in giving you quite a good idea about what is going on during pultrusion. The process itself is very interesting, is very appealing in several sectors from the point of view of the costs and productivity. So probably in the next years we will keep on seeing new applications of the pultrusion process. Clearly, in order to properly set our pultrusion line, a careful consideration of different aspects is needed. If we want to define the best parameters for pultrusion, we should take into account the reactivity of our resin, the physical and mechanical properties of our material, the pulling speed that we want to use, and so on. And of course also something related to stress and distortion. But I have to say also that now there are several powerful softwares that can be used to recreate our manufacturing process in a virtual environment and support our decision. So in the past years, pultrusion experienced several developments. We have new variants but I think that the history of pultrusion is just at the beginning, and maybe in the future we will be able to realize, using this approach, some very complicated shape and process more and more material. So thank you for your kind attention. I hope that you enjoyed this talk. In case you have any questions or you want to interact and talk about pultrusion, my contact details are there. Feel free to drop me an email and I will be happy to stay in touch and discuss with you about this topic. Thank you.